the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are just starting their pathway through linear algebra, and you have just been introduced to row equivalent matrices, the augmented matrix for a linear system, row operations, and kind of a review of systems of linear equations. So this should round out kind of the first section of material that you're going through. And I'm really happy that one of my students this semester let me know that, well, this video was missing from my video series because this is actually a very important topic, even though somewhat fast. It is super important to talk about, so let's do it. The existence and uniqueness of solutions to linear systems. As I told my students today, in fact, most of mathematics is very much concerned with these two problems, or these two questions: existence and uniqueness. Does a solution exist? If so, is it unique? So the questions of the existence of solutions to a linear system and subsequently the uniqueness of those solutions are vital in this course, actually in all of mathematics. Just as we're more concerned with the convergence of a series than what the series converged to in our integral calculus course, we commonly focus on whether a linear system has a solution in linear algebra rather than what that solution actually is. And by the way, if we do end up finding out that a system has a solution, we'd like to know, well, is it unique? And this is going to be a massive theme through this course. So like I said, I'm super happy I was informed this video was missing. So let's consider the following two augmented matrices. You can see them right here. They actually have variables in them, right? Or I would consider those parameters, not variables. But anyhow, you have one matrix here, -2 T9, 4, 1, 18, and then the other one, 7, 3, 8, 7/3, 1, and T. Our first task, for what values of T does each augmented matrix represent a system with a unique solution? And then identify characteristics of an augmented matrix that yield unique solutions. This is so important. I can't believe I didn't record this. Shame on me. Well, let's take a look at this very first matrix. I'm going to write it down. And I personally like to write an augmentation bar in there, although you don't necessarily have to. I just personally prefer to do that. Let's go ahead and perform a single elementary row operation on this matrix. I'm just going to go ahead and do row replacement to remove that entry right there. Let's take 2 times row 1 and add it to row 2. Remember, solutions are invariant under elementary row operations, so this will not change the solution set of the underlying linear system. In this process, row 1 is actually not going to change, but row 2 definitely is. We'll take twice row 1, so we get -4, and we're going to add that to row 2, +4, so that's 0. Twice T is 2T plus 1, that's just 2T plus 1. There's nothing you could do about that. And finally, twice this 9 is 18, plus 18 is 36. Now let's take a look at the underlying linear system. Remember, these are row equivalent matrices right here. And from the previous video in this lecture series, we know that if matrices are row equivalent, then the solution sets of their underlying linear systems are the same. In other words, the linear systems they represent are equivalent. So let's take a look at the linear system represented here. Now you're taking a look at that and I know what you're thinking. You're probably thinking, man, there's a lot of variables in there. There are 3 variables. Nope, there's actually only 2, x sub 1 and x sub 2. T is just a parameter. It's something that we get to play with to figure out what breaks this system, or better yet, what makes this system solvable. Well, how would you solve, let's say, x for x sub 2 here? Honestly, you would divide both sides by the coefficient of x sub 2. And that means that coefficient had better not be 0. So to be able to isolate x sub 2, we require that that coefficient is non-zero. Think about it this way. If that coefficient was 0, then this equation right here would say 0 times x sub 2, or in other words 0, should equal 36. Do you see a problem with that? Because I do. I definitely see a problem with that. So as long as that coefficient is non-zero, we can guarantee we could divide by that number and we'd find out identically what x sub 2 is. So to have a solution, specifically a unique solution, we require that t not equal -1/2. Okay, great. T cannot be a -1/2. So for this first equation, t can't be a -1/2. Got that. Well, what about that second equation? Or I shouldn't say equation, I should say this second augmented matrix. What value of t or values of t will guarantee that we get a single solution to the underlying linear system? Well, again, I'm going to do a little bit of magic down here. And the first thing I'm going to do, just because I want to, I'm going to go ahead and multiply row 2 by 3. I really dislike fractions, so it's just a habit I have. You don't have to do that, but I'm going to do it. It's a simple elementary row operation. So the solution sets for these underlying systems should be the same. They should be invariant under that elementary row operation. Note here, these two rows are almost identical. And in fact, if you were to go ahead and do a row replacement here, that is, if you were to take negative row 1 and add it to row 2 to become the new row 2, you would get the following. Now, taking a look at that, you might not know what is going on here, if there's a solution or not. Remember, we're hoping to have a unique solution, and you should be able to see that we will not get a unique solution once we transform this into a linear system. If you take a look at that resulting system of equations, remember, t is just some parameter I get to adjust here. And in fact, I can easily tell you this equation will always be a contradiction as long as t is not equal to 8/3. If t is equal to 8/3, then this is an identity statement, the second equation is. Otherwise, it's a falsehood. For example, if t is 1, then you get 0 is equal to -5. That just is not true. So there's only one case where this will be true. This is only true if t is equal to 8/3. So I have that restriction already. If t is not equal to 8/3, we've got a problem, right? We have 0 is equal to a non-zero number and the world blows up. So we have a restriction on t just to get to a system that might have a solution. However, if that's the case and we set t equal to 8/3 so that this bottom equation is just 0 equals 0, our system boils down to just this one equation, a single equation with two unknowns. And we know the graph of a single equation with two unknowns is a line. It's just like, let's say, 7x plus 3y is equal to 8. That's a line. That's the equation of a line. And so therefore, there are an infinite number of solutions. That is, to answer the question that we were asked, for what values of t does each augmented matrix represent a system with unique solution? Well, for the first one, we have all values of t will yield a unique solution except for t equals -1/2. And for simplicity, I'm going to call this matrix A sub 1 and this matrix A sub 2, only because the letters A and B and stuff like that are taken in this discussion already. So for the first augmented matrix, we know that that linear system that underlies that augmented matrix has a unique solution as long as t is not equal to a -1/2. That upside down capital A just means for all. So for all t not equal to -1/2, we have a unique solution. But for A sub 2, there's no value of t. Or in other words, the empty set. No matter what we choose for the value of t, there's just not a unique solution to the underlying linear system. So let's talk about the key characteristics that yield unique solutions to linear systems. Well, that's pretty easy if you look only at the first example, the A sub 1 matrix. This was the A sub 1 after we did row reduction. And what was nice about this was we got down to what we would call a triangular form with the coefficient matrix right here. And when we got down to that triangular form, we found out that, oh, the represented linear system that's underlying the augmented matrix has one equation with two variables and another equation with a single variable. We just required that the coefficient of that single variable not be 0. Because again, if that coefficient were 0, we'd have 0 is equal to 36. So right then and there, I can easily say we can't have a row in the augmented matrix of the form 0, 0, 0 on forever, or not forever, but a bunch of zeros, and then the last entry being a non-zero value. Because if we had that situation, the related equation to that would be 0 is equal to C, where C is non-zero. And that's a problem. The world blows up when 0 is equal to something not 0. So that is a characteristic of augmented matrices that prevent us from having unique solutions. But what does that mean and where does that leave us? Because remember, we're trying to find out the key characteristics of an augmented matrix that yield unique solutions, not the characteristics that don't give solutions at all. We know we don't have a solution if we have a row of this form right here. But what if we don't have a row of that form? Does it mean immediately we have a unique solution? The answer to that actually is tied to the second system. If you take a look at the second system, that bottom row, it's 0, 0, and then some possibly non-zero entry. And yet this system, if we forced that bottom entry, the 3t minus 8, to be 0, that system would have an infinite number of solutions because remember, it ended up being a line. How did we force it to have an infinite number of solutions? We forced this entry to be 0. So we have these two situations. If you have a row of this form right here, then there are no solutions because obviously 0 cannot equal a non-zero value. And if we have a row of the form 0, 0, and so on and so forth, all the way through that row, all the way to 0 at the end, we might have an infinite number of solutions. Now I know what you're thinking. Wait a second. We've just shown that if that bottom right element in this augmented matrix is 0, this underlying system has an infinite number of solutions. But that was only this underlying system. There are many other matrix structures where you could have a row of zeros in that augmented matrix and you have an infinite number of solutions, that can happen, or one solution, that could totally happen, or no solutions, that could actually happen as well. So this was just an example here showcasing, oh, all right, so in this case, if that highlighted piece was 0, we'd be only left with this guy right here, and we'd have an infinite number of solutions because that's the equation of a line. However, if I changed this matrix to be, let's say, 3 equations and 2 unknowns, and we said, oh, well, let's go ahead and let t equal 8/3. Well, if you let t equal 8/3, that would turn into 0, yet you have 7x sub 1 plus 3, x sub 2 is equal to 8. That's the equation of a line. But we also have x sub 2 is equal to 1. So we know what x sub 2 is. Plug that in here and you'll find out what x sub 1 is, and there is a single solution to that system. So just having a row of zeros does not mean that you have an infinite number of solutions. It totally depends upon the structure of the given matrix. However, on the other hand, if somebody gives you a row in your matrix and it looks like this, 0, 0, 0, 0, 0, 0, and let's just pretend 10, then they're telling you, oh, by the way, to solve this, you have to prove that 0 is equal to 10. That doesn't happen. There's just no solution. So immediately I know if my matrix has any row of this form, if my augmented matrix has any row of this form, I immediately know there's no solution. Now, honestly, this doesn't really help us out a ton, but one thing we can say about the unique solution situation, if we have the same number of equations as we have variables, well, then that actually can constrain it enough where we can have a conversation. So notice I have 1, 2 equations and 1, 2 variables. The same thing with the second system. It represents 2 equations with 2 unknowns. Okay, so if we restrict our conversation to n by n systems, or systems that have the same number of equations as they have unknowns, then you can sort of easily discuss the key characteristics for finding unique solutions. To get a unique solution to such a linear system, it has to be able to be row reduced to a diagonal form like this, where you don't have a row of zeros and you don't have a row of all zeros with the last entry being non-zero. Let me write that down actually, because I think that's important. A linear system of n equations and n unknowns has a unique solution as long as its augmented matrix is not row equivalent to a matrix with a row of zeros or a row of the form 0, 0, 0, 0, 0, C, where C is non-zero. That last piece right there would just tell us that 0 is equal to a non-zero number. That's a problem. There'd be no solution to that. And the previous one, a full row of zeros, means that you have one variable that you cannot identify in your linear system. It's basically this situation right here, where we can't identify the x sub 2 variable because its coefficient is 0, and therefore that leaves us with too many variables and too few equations, and hence there's an infinite number of solutions. Now, this discussion seems convoluted only because we don't really have the mathematical technology to do this in an easier way, but we will champion on and continue forward with this example. For what values of t does each augmented matrix represent a system with infinite solutions? Now, just to remind you, the very first augmented matrix was this guy right here. We did row operation, a single row operation to get to this point right here. To have an infinite number of solutions, we would need to completely get rid of one variable in the linear system. That is, we would need to reduce this system of two equations to a system of one equation with two unknowns. That means it would just be a line, an infinite number of solutions. So how do you do that? You force that lead coefficient to be 0. If t is a -1/2, we get that 0 is equal to 18. Now remember, to have a solution, we would like this to not be 0, so we could divide by it, move it to the other side and solve for x sub 2, and then solve for x sub 1. But how do you get an infinite number of solutions? I'd like to turn off that bottom equation to get an infinite number of solutions by just keeping this top equation. Unfortunately, there's no way to turn off that bottom equation. If you think about it, there's only two options. Either x sub 2 has a non-zero coefficient or x sub 2 has a 0 coefficient. If x sub 2 had a 0 coefficient, you'd have 0 is equal to 18. There'd be no solution. And that's not what we're looking for. We want an infinite number of solutions. If x sub 2's coefficient was non-zero, we'd have one solution. So there's no choice of t here that will give us an infinite number of solutions. I'll just say it this way. No matter what, the linear system for a sub 1 will never have an infinite number of solutions because we cannot completely zero out that bottom row. On the other hand, a sub 2, we can actually zero out that entire bottom row if we allow t to equal 8/3. So again, if t is equal to 8/3, the linear system for a sub 2 will have an infinite number of solutions because we would reduce the complexity of the system to only be 7x sub 1 plus 3x sub 2 is equal to 8. That is a line, and therefore it has an infinite number of solutions. So what is the lesson that we learn from this? Identify characteristics of an augmented matrix that yield infinite solutions. Well, I'm going to steal a lot of the language from the previous example. So pasting in what we had before and kind of changing the language, we're going to still stick with the theme that we have n equations with n unknowns. All bets are off if you go outside of that realm for now, but a linear system of n equations and n unknowns has an infinite number of solutions if the augmented matrix for that system is row equivalent to a matrix with a row of zeros. Again, I just want to reiterate, we're only sticking to systems of n equations and n unknowns. You go beyond that to rectangular systems with m equations and n unknowns, where m is not equal to n, then all bets are off. We have to change up our language, and that's why we move forward in linear algebra to invent more robust mathematics that can be used for those situations. So now we finish out this video with just the last couple examples. These are actually the fastest ones. For what values of t does each augmented matrix represent a system with no solutions? And I wrote down the matrices right there, and we happen to know there's just no solution if this number is 0, because 0 can't equal 36. So we know we don't have a solution if 1 plus 2t is equal to 0, or in other words, if t is a negative 1/2. Great. What about the other system? Well, again, this one kind of also jumps out at us because we have a row of zeros. That's like 0x sub 1 plus 0x sub 2 is equal to this number, which might actually not be 0. So I would love it if this number was non-zero, so we didn't have a solution. And to get that to be non-zero, we just say, I want 3t minus 8 to not be 0, and that will imply that t is 8/3. Those are the values of t that make both of those systems that relate to those augmented matrices unsolvable, or in other words, inconsistent. What are the characteristics that create an inconsistent system? Pretty easy. It's that you have a row of zeros with a non-zero last entry. That is, again, a row of zeros with a non-zero final entry. Now, of all the conditions, this is the one that I think is the easiest to understand, because if you have a row of all zeros except for the final entry, you're basically saying, hey, 0 is equal to some non-zero number. That can't be true, and so therefore there's no solution to that system. Now, I chose this example, as convoluted as it is, to showcase something very, very important. This example focused on, does a system have a solution, and if it does, is the solution unique, or does a system not have a solution? That's called the existence and uniqueness question. Does there exist a solution or not? And if so, is the solution unique? All right, you should probably watch this a couple times, honestly, because there is a lot of detail in here that can be easily glossed over or ignored, but it ends up being primary and very important in linear algebra. All right, that's enough for me. I hope you have a great day. And be good to human beings.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just